If a thing is happening slowly, if anything is in quasi-static equilibrium, that process is a reversible process. If there's a cylinder having a piston, it comes up all of a sudden, that's an irreversible process. And if you're allowing it to come up very slowly, and that process is reversible process. Why? We have seen this before. Now, for this thing to occur very slowly from T0 to Tf, then this has to be in quasi-equilibrium with its environment. Considering the environment temperature was T0 and the gas temperature was also T0. Now you have to increase the temperature very slowly. That means dq will increase the temperature very little, that it is almost in quasi-static condition. So when dq is given, then because the volume is constant, as per first law, delta U is equal to Q plus W. Volume is constant, that means work is 0. Fine. Delta U for ideal gas is NCV dt. We know this. So Q will also be equal to NCV dt. So dq, or the small amount of heat that you have given, is equal to small amount of change in internal energy. So dq is equal to NCV dt from first law of thermodynamics. So you have to integrate this. Now you have a good looking expression that can be integrated, because n and cv are constant, and dt, integral of dt by t, you know, don't you? Integral of dx by x is ln x. So will be integral of dt by t, ln t, from t0 to tf. So this is ncv ln tf by t0. This is change in entropy. So now you can have an expression. Now you have an expression for change in entropy for an ideal gas in the case where volume is constant. So someone gives you the final temperature and initial temperature. Putting that final temperature and initial temperature, you can quickly find out the change in entropy. And if the change in entropy is positive, then the process will be spontaneous. That means if the temperature, final temperature is higher, that means it is getting heated up, then that will be spontaneous. If the final temperature is lower, that means this ln term will be negative. That means you are taking away the heat, and that will be non-spontaneous, because spontaneously this ideal gas is not going to give away its heat. That's the significance. That's the delta S. Okay. Similarly, let's deal with other situations. In this case, what happened? We took the volume to be constant. We can also take situations in which pressure is constant. In this case, the formula of delta S came out to be NCV ln T final by T initial. Fine. There could be other situations in which the pressure is constant. If we have a cylinder having a piston, and this piston is always having an atmospheric pressure from outside, so it will always have a atmospheric pressure from inside in equilibrium state. So the pressure inside is always going to be constant. So when you have a constant pressure, so in that case, if you know that amount of heat that will be given, when Q amount of heat is given, the rise in temperature of a system when the pressure is constant is NCP dt. Alright. Delta U is equal to Q plus W. This you know. Now for an ideal gas, the temperature, the increase in internal energy is always equal to NCV dt. This we discussed before, and work is equal to, suppose this is dq, then small amount of work, dq is equal to minus pdv. Now this is the definition of work we have seen, minus pdv. Now when you take this on this side, then dq becomes ncp dt. Fine. Now using this, dq here is ncp dt. So in the definition of entropy, ds is equal to dq by t. So this is dq and this is t. So ds will come out as ncp ln t final by t initial. So this is going to be the formula for change in entropy in case of isobaric process in which pressure is constant. Similarly, we can have other processes in which temperature is constant. Suppose this is an isothermal process. Now in this process, because the temperature is constant, so as per the first law of thermodynamics, delta U is equal to Q plus W. Temperature is constant and internal energy is the function of temperature only. So this delta U is 0. Fine. So Q plus W is equal to 0, or Q is equal to minus W, and work done is minus PdV. So minus W is PdV. Small amount of heat, small amount of work. Fine. Now the dQ is PdV. Fine. So now we'll go back to the expression of formula of entropy. So ds is equal to dQ by T. dQ is equal to here dQ is equal to PdV by T, and P, as per the ideal gas equation, because we have taken ideal gas, is nRT by V, and dV by T remains as it is. This is P. PV is equal to nRT, P is equal to nRT by V. T cancels out and we have dV by V. So integration of this is ln V, and putting the limit, delta S will come out as ln Vf by initial volume V naught. So these are the three formulas for three different cases. If you have constant volume, this will be the formula for calculating entropy. If you have constant pressure, if you have constant temperature, you have to work this out on your own. Consider what we have used is basically three things: ideal gas equation, the thermodynamics first law, and thermodynamics second law. That is ds is equal to dQ by T. Now you should be able to get to all the formulas very quickly, and you have to practice them, deriving them again and again, so that they come on your fingertips. If you don't do much practice, then there's a high chance in exam, even if you know problems, you will miss them out because of less time. So practice them so that you get your speed during solving the problems.